Hello, I am Professor S. Shankaran in the Department of Metallurgical and Materials Engineering. We will now look at some other details. The stress strain curve of a sample loaded and unloaded in a continuous cycle would resemble the loop OBICO shown in the figure instead of a parallelogram OAI-A-O. Okay. Of course, the shaded area, this I have already told. The elastic energy stored during the loading cycle is represented by the area under OBI. This is one way of looking at it. So, OBI, this is a area, elastic work done, and this is nothing but integral sigma dE, and has got the unit of energy per unit volume. The energy recovered during unloading is represented by the area under ICO. So, this area. So, work recovered, work done. Okay. So, this minus this will give what? So, the energy dissipated in a single cycle in an area enclosed by the hysteresis loop, it is equal to the area under the loading curve minus the area under the unloading curve. So, this minus this will give the small hysteresis loop which I just showed in the elastic hysteresis loop. So, that is what it is. So, this is what is written here. Okay. So, the difference between elastic work done and the elastic energy recovered is equal to energy dissipated, which is the area enclosed by the hysteresis loop. So, any event we can correlate. So many events we can talk about, right? Migration of atoms, thermal energy, right? We said stress and strain and so on. This is a general description of energy dissipation or energy elastic work done, okay, in a hysteresis loop. So, that is a general description. Even though the hysteresis loop in many materials may enclose a very small area, the elastic hysteresis effect is important if the material is subject to rapid vibration. So, we have to remember that even though the area enclosed in this kind of curve is very small like this, it is important when the material is subjected to rapid vibration. For the total energy dissipated in a given period of time is the product of area per cycle and the number of cycles. So, this also we will see as we proceed. We will look at some of the case studies. So, what is shown here? The energy dissipation per cycle as a function of frequency. So, we were talking about loading, unloading, this kind of hysteresis loop. We arrived at a physical meaning of what is hysteresis loop or elastic energy hysteresis loop, but that has to happen in particular frequency. So, what is the frequency at which things will happen, or in other way, at what frequency the maximum energy dissipation will happen. Okay, that is also important, right, depending upon what you are looking at, right. So, this is what we are going to discuss now. So, this is energy dissipated per cycle versus number of different frequencies, and then you can see that this particular small graphs which shows that the different positions of the first diagram, you can just go back and relate A and I position, and then how the frequency is different from different positions, right. For example, if it is okay, what we can do is we can just look at where this 0 to I position, and 0 to I position can be of enclosing a small hysteresis loop at a different frequency. This is the lowest frequency, slightly increased frequency, it is a medium range frequency, and again it is coming to the very high frequency. See, what you see from this in general, the lowest frequency and highest frequency is not dissipating maximum energy. So, only at particular medium range of frequency, your energy dissipation is maximum. Okay. So, we will see some of the physical events, how they are relating to this concept and how it is helpful. If the frequency is very low, the cycle may be almost completely isothermal. So, in our case, what we just said, a crystalline material is very slowly stretched from 0 to the position I, in which case the area enclosed by the hysteresis loop is extremely small. So, in fact, it is a straight line almost here. Okay. If the frequency of loading or unloading is very high, the loading and unloading paths may be almost completely adiabatic. Okay. And again the area enclosed by the hysteresis loop is very small. So, here, so this is isothermal I, this is adiabatic A. In both the cases, the hysteresis loop is extremely small. At some intermediate frequency, the area enclosed by the loop is at a maximum. So, this is some intermediate frequency. Okay. So, now how do we understand this graph? It is a very general description we are giving. So, now we have to look at some physical events, for example, atom jumps, defect migration, thermal energy migration, whether it fits into any, what kind of frequency and how much of energy can be. So, we can easily relate, okay, all the physical events to the energy dissipation. Okay, it could, which will involve any part of your heat treatment or processing sequence and so on. This is very important idea. Okay. So, one classical example we will take, the stress induced diffusion of carbon in iron, very well known phenomenon here. This is a BCC lattice, in fact it is a unit cell, 2 unit cell which is stacked one upon the other, it is a BCC unit cell, and where you have this carbon atom is sitting here in the edge center, okay. And then this unit cell is getting stretched in a tension mode, okay. Then what can happen? That is a general description. So, what can happen if you just stretch it, the effect. Now, please remember, we are talking about elastic deformation. We have not crossed that elastic. We are still in elastic deformation, thermoelastic effect, right. So, if you stretch it elastically, what happens with this axis will get elongated and Poisson ratio effect will be there. So, this will get contracted, right. So, what will happen to the atom sitting here? It will also come subjected to some constraint. So, it will try to escape from the constraint or relax to a very comfortable position, wherever this this is pushing from there. So, this is getting elongated. So, there is one possibility that this carbon atom can jump from this position to this position when we stretch it in a axis perpendicular to this. Yeah, this is perpendicular to this section. So, here what is that we are talking about cycling? The cycling is the atom has to jump from one position to the other position and relax, come back. So, that is the event we are taking it up. Okay. So, the diffusion of interstitial atoms in a metal lattice can give rise to elastic hysteresis, exactly as the diffusion of thermal energy in the thermoelastic effect. Okay. And here the stress induced diffusion of carbon and iron. Carbon atoms occupy a random position at the centers of edges of the body centered cubic iron lattice. In the positions they slightly distort the unit cell. So, of course, when you have this any atom, foreign atom which sits there in the interstitial positions, then you will try to distort little bit. On this account, only occasional carbon atoms, well separated and randomly distributed in 3 perpendicular directions, can be accommodated without creating highly stressed state throughout the entire lattice. Okay. So, what does it mean? For this, not all the carbon atoms will undergo jump what we are discussing about. Uh, Only a carbon atom which are subjected to constraint will jump, and also will try to go to the new position where there is no other constraints. Okay. So that is what it is shown here. So this is also one of the a classical example of this thermoelastic effect. When these two when this kind of lattice is stretched, the diffusion of carbon atom from the constrained position to the new position is also as a function of elastic strain. Okay, and then it relaxes back to its original position is also a cycle, in a cycle. Okay, depending upon the temperature, or it can happen with even temperature also, a phase transformation, temperature, elastic strain, thermal energy or vacancy motion. That's what we said. Migration of defects, thermal energy migration, or the atoms and so on. So this is one classical example. The two instances of anelastic effect discussed above, what are this? This is one, the other one is the crystalline material getting stretched up. Those arising from the fact that the finite time is required for the diffusion of thermal energy or the interstitial atoms are adequate to establish certain general features of anelasticity. So looking at these kind of events, physical events, there are salient features one can list out. What are the general features of anelasticity, right? So that's what we are just going to look at. It is more descriptive, but very important. So that's why I am trying to stop and then repeat certain statement again and again. Anelastic effects also arise from motion of substitutional solute atoms. We have just discussed about interstitial atom, that is carbon in iron lattice. It can also arise from motion of substitutional solid atoms, grain boundary effects, motion of dislocations, intercrystallite and transcrystalline thermal currents. So we made general statements in the previous slides. Now we are getting to little more specific, right? We just say thermal energy. Now we are talking about intercrystallite and transcrystalline thermal energy currents. We are talking about. We just generally said defects. Now we are talking about dislocation, motions of dislocation. We just mentioned about atoms. Now we are talking about substitutional solute atoms in addition to interstitial atoms. So we are getting into specific ideas. Such thermal currents have their origin in elastic anisotropy typical of most crystalline materials. So this is more relevant to crystalline materials. Adjacent grains strain differently and thus heat up or cool down to different extents under stress. So this also we will see when we go to the plastic deformation or polycrystalline deformation. When you have two different, several grains will be oriented at different directions, and then you are going to stretch it in one particular direction or apply the load in particular direction. All the grains will try to rotate, accommodate, strain each other, okay, and that's what it is. Adjacent grains strain differently. So depending upon the slip characteristics, we will see depending upon the critical resolved shear stress and so on, everything get realigned or stretched towards the stress axis or loading axis. In that activity, they get heated up or cooled down to different extent under stress. Heat transfer then occurs from one grain to other. So that is one event. Whatever the mechanism by which anelastic effect is produced, the maximum energy dissipated when the time per cycle is of the same order as the time required for the process causing the anelastic effect. Very important. It looks a little confusing, but then when we just look at a concept like relaxation time and all, this statement will become much more straightforward. The time per cycle is of the same order. It should be the same order of the time required for the process causing the anelastic effect. Okay. So very important ideas. we have to just relate this to physical events, then it is interesting. Otherwise, it looks more kind of a text. In carbon diffusion, for instance, the maximum occurs, that is the inelastic effect, when the time per cycle is of the same order as the time required for the diffusional jump of the carbon atom. The times characteristic of the previous process giving rise to inelastic effects vary widely. Okay. For example, near room temperature, the peak of energy dissipation due to interstitial atom occurs at a frequency of the order of 10 to the power minus 2 to 10 to the power minus 1 cycle per second. Okay. So, what is that we are talking about? We are talking about the maximum energy, that the peak of energy happens when the frequency of this order. What is the physical event? Interstitial atom jumps. Whereas, intercrystalline thermal currents occurs at about 10 to the power 5 cycles per second. Look at the different frequencies. See, now you can just relate these frequencies with the diagram what we have shown, right? We have just seen that the energy dissipation at different frequencies, right? So, this is one classical example, right? So, this frequency is very different compared to this frequency, and the grain boundary shear at about 10 to the power minus 8 per cycle per second. Okay. So, every event will have a different range of frequencies, but even if you take a grain boundary shear alone, this one particular physical event alone also will have the relevance to that diagram. Not all the frequencies will produce a similar kind of dissipation, only a particular range of frequency will dissipate the maximum energy. So, that's something you have to remember. The peak of a curve of energy dissipation versus frequency, this is what we have seen already, occurs for a frequency at which the time per cycle is comparable to the relaxation time for the process responsible for the energy dissipation. So, this point is almost what we have just made a statement just before. So, now to have some more clarity, we are bringing another parameter called relaxation time. Okay. So, what relaxation time of what? Relaxation time for the which is causing that as a whole thermoelastic effect, that is a cycle, right. So, that is relaxation time. So, the average time required for the internal rearrangement which tend to occur during the cyclic stressing. So, what is relaxation time? We will just see now. It is desirable and often permissible to describe the time dependent component of elastic strain. So, this is time dependent component of elastic strain with a single number. We would like to give some number for this quantity, relaxation time tau. It is designated as a tau. So, how do we understand this concept? So, look at this diagram. So, the diagram will look little complicated in the very first look, because too many writings on them. So, do not get confused. So, we should also relax. So, then you will be able to catch this. What is shown here? Elastic strain epsilon versus time. Okay. Do not pay any attention to the writings. So, now we have two types of two different part of the curve. One is t is equal to 0, and it is almost like constant t is equal to here, and then slowly it relaxes to one point, and again unloading and then relaxes. So, instant loading or adiabatic loading, you may whatever the way we can look at it, then the elastic strain EU is reached all of a sudden, that is t is equal to 0, and then it relaxes. It continuously, the load is on. So, but it relaxes, the material relaxes to the maximum, that is ER. ER is relaxed strain, and then suddenly unloaded, t is equal to t1 and then slowly relaxes, asymptotic. This is asymptotic, right? We just discussed about this behavior, asymptotic. Okay. So this is the physical event you have to just first understand. The next point is, this is what I just said. To understand the meaning of this concept, consider a specimen which has a load suddenly applied at t is equal to 0. The specimen suffers an immediate elastic strain, which is unrelaxed strain and correspond to adiabatic strain EA, okay, of the figure. Okay. And then the load is maintained, the strain gradually increases with the passage of time toward the value ER. Okay. Actually, what I think it is adiabatic strain epsilon A is also is equal to E epsilon U. That you can either you use it as 1 U EU or EA is fine. There is some inconsistencies here. Immediate elastic strain epsilon U, and this is also equivalent to epsilon A of the original figure we have. The introduction we have just used to explain the concept of isothermal loading and adiabatic loading. We have used epsilon A, so that is why it is brought here. It is equivalent to epsilon U, so you don't have to get confused with that. So if the load is maintained, the strain gradually increases with the passage of time toward the value ER, which is the completely relaxed strain. So that's why I said it's a relaxed strain and correspond to the isothermal strain EI of the figure. Yeah. If the load is suddenly removed at t is equal to t1, the specimen undergoes an intermediate elastic contraction. This is intermediate contraction again, EU, and with the passage of time slowly approaches its initial strain free state. So this is asymptotically coming down. Okay, so now we will just look at a little more description of this. How do we understand that relaxation time? The time dependent component of elastic strain may often be approximated as an exponential function of time. So this is one assumption we have to understand here. If A is a fraction of the total strain which lags behind the application of load, that is, A is a fraction of the total strain which lags behind the application of load, A is equal to ER minus EU by ER. The time dependency of the loading curve may be expressed as by this expression, epsilon is equal to epsilon R times 1 minus A into e to the power minus t by tau. This is for the loading. For unloading, epsilon is equal to A times epsilon R into e to the power minus square bracket t minus t1 divided by tau. This is for unloading. Okay. Now, suppose we are talking about a cyclic loading, right? Relaxation time. That means any physical event which is going to complete, right? Loading and unloading. That means it has to attain the equilibrium strain or isothermal strain, and it has to come back to the strain free region. So that cycle it has to complete. So the relaxation time is the time dependent component of elastic strain is related to relaxation time. So if you just take this particular equation, suppose if I am putting t is equal to 0, t is equal to t1. These are the two times we have just looked at in that figure, right? Suppose if I replace t by tau, that means what? That particular physical event has completed. Okay. So if you replace t is equal to tau, what happens? Then it becomes 1 by E, okay, 1 by E times the rest of the whatever it is. So, you just look at this point alone, then you will get the complete idea. Then we will go back to the figure, then understand. Suppose if you replace, if the T is, if the complete event is over, then tau is, T is equal to tau, okay. Or before that it could be anything, it could be T is equal to 0, T is equal to T1, T is equal to anything. But the event is over, that physical event is over, then T is equal to tau, we can put, then it is 1 by E. So, that is what it is shown here, where tau is the measure of the time required for the relaxation. The time required for the time dependent component of the strain to raise to within 1 by E of its final value of the loading, or to decrease to within 1 by E of its initial value on unloading. So, what is the meaning? That is what shown in that figure. Now, we will go back to the figure. You see, we have now just put, suppose I am interested here, this is the tau, this is the measure of tau here. So, this is a relaxation time. It is not completely relaxed strain, it has not reached here, but it is somewhere here. So, here if I want to look at it, that will have so much of the fraction of 1 by E, that is what it is, right. The strain is a fraction, but it is within the 1 by E, it is not completed, it is 1 by E is after completion. So, here at this point tau is a fraction of 1 by E. Similarly, you can see here also it is relaxed here. So, here also it is a fraction of 1 by E, and in between these sudden changes given, it will be equivalent to this expression. So, that is how you should look at it. Then the meaning of relaxation time is easily visualized from this. So, this can be of any range. So, it can, the tau can be here or tau can be here, but still it will be within that yeah, I will go back to this. So, it will be still within the 1 by E of its final value on either on loading or unloading. So, this is what we are just seeing in the figure, in the loading part as well as unloading part. Okay, so that is quite important concepts, relaxation times, and this is, we will be using these parameters in the deformation behavior of non-crystalline materials, semi-crystalline materials, and so on later, right. Anelasticity, wherever we discuss this property, these parameters will be much useful. So, if you know it from the beginning, then you do not have to just think, and there you can just concentrate on the material and microstructure and so on. So, these are the some inputs you require in the beginning. So, we will stop here and we will continue in the next class. Thank you.